Chapter 5, Section 2 is about relations and functions. So by the end of this lesson, you should be able to identify relations and functions, and you should be able to evaluate functions. So we have some vocab words. We haven't had some of these in a while. But we have something called a relation, which is a set of ordered pairs, or numbers that are somehow related to each other. Function is a word we've had in the past, but it's a relation that assigns exactly one output value for each input value. Something called the vertical line test says if any one vertical line passes through more than one point on a graph of a relation, then it's not a function. And then finally, something called function notation. It's a way that we write functions, and it looks like this right here, f with parentheses x. And this is said f of x, not f times x. So for all of these, remember, you need to come up with some sort of example. So a relation is a set of ordered pairs. So they gave you an example, the age and then the height for each of these giraffes. So we can write the ordered pairs like we did down here. We tend to use squiggly brackets like we see here to group these ordered pairs together. So recall from lesson 1.4 that a function is a relation that assigns exactly one output to each input. So what exactly does that mean? So let's pretend we have a bunch of pizzas and a bunch of houses. We'll think of the pizzas as our inputs and the houses as our outputs. So pizzas go out to houses. So in this first example here, we have pizza 2 going to house A, pizza 4 going to house B, pizza 3 going to house C, and pizza 1 going to house D. So for each one of these, there is an input and an output. Now, this one can be modeled. House A got pizza 2, House B got pizza 4, House C got pizza 3, and then finally House D got pizza 1. So if something like this can be modeled, this is a function. Remember this definition from back here. It assigns exactly one output to each input. So now if we go back and do the next one, where we have House A right here ends up with 2 pizzas. This again can be modeled. It's totally okay for one house to order more than one pizza. Maybe they have friends or family over. And it's totally okay for House D not to eat any pizza. That happens some nights. So this is also a function. You have one output for each input. Now, some of these are repeated, where 2 goes to both A and so does 1. But down here, if you notice, we have a repeat of 2 pizzas trying to go to one house. Pizza 1 is trying to go to house A and to house B. So if we try to model that, there's really no place for pizza 1 to go. It doesn't know whether to go to house B or house A. Where pizza 3 went to house D, and pizza 2 went to house C. This pizza shouldn't be here. No one ordered pizza 4. So because of that, it's easy for us to see that this is not a function. These 2 inputs right here gave you different outputs, and that's not allowed. So in order to see this, we use something called a mapping diagram. And a mapping diagram has us split inputs and outputs up. And remember, inputs are x values and outputs are y values. And we make these nice, neat little boxes. And we just list our inputs and outputs. We tend to list these in numerical order. So we have a 3, an 8, a 9, a 3, and a -4. Now because 3 is already on here, I'm not going to write it on there twice. And then list all of our outputs. So I get out a -2, I get out 1, a +2, a 3, and a 0. Now the mapping part of this says that we are going to map one onto the other. So if I put in 3, I get out -2. If I put in 8, I get out 1. If I put in 9, I get out 2. And if I put in 3, which was back up here again, I get out 3 that time. Put in -4, I get 0. Now stop and think of this as pizzas and houses again. Is this a function? Does this work? And the one that we really want to concentrate on is this right here. So if we think about this, this is one pizza trying to go to 2 different houses. It's trying to go to that house and that house. So that physically can't happen. One pizza can't be split up. So this is not a function. I'm going to have you do this one as your can you prove it. So if you want, you could stop right now and do it, or you could wait till the end. Now here's our vertical line test. This is another way to tell whether a relation is a function if we have a graph. So the vertical line test means that we're just going to draw vertical lines. And you're going to draw a vertical line through all of your points. And if this vertical line crosses through 2 or more points, that right there means it's not a function. Because this point right here is at 3, 0, and this point right here is at 3, 2. So that means that house 3, or pizza 3, sorry, is trying to go to 2 different houses, and that can't happen. Another thing to do is just pass your pencil across it like they're doing here. If your pencil crosses more than once, like that, it's an easy way to say it's not a function. So let's do an example. So let's draw ourselves a nice little graph. And plot these points. So the first one I'm going to go over 4 down 2, over 1 up 2, 0, 1, and then -2, 2. So one thing that people get confused on is there's a lot of the same numbers in here. And sometimes it's okay to repeat numbers and sometimes it's not. So the vertical line test is a quick and easy way for us to say, does it work or doesn't it? So if I draw vertical lines through all of my points, these green vertical lines only pass through 1 point. So that means that this is a function. For every input, there's only 1 output. And again, I'm going to have you do part B as your can you prove it. So you could pause it or wait until the end. Now, evaluating functions. Evaluating has the word value kind of hidden in it. That means we need to find a number for our answer, find a value. So a function can be thought of as some type of machine that assigns one output to every input. And this is function notation. So this f of x, remember that's how you say it, is just the name of the function. We like to use f because of function, but sometimes we use g, sometimes we use h. But what is ever inside of these parentheses, this x, this tells you what number to plug into the function. So x is just kind of a placeholder. This whole thing right here is the output of our function. Whatever letter or whatever number we get here is our output. Usually this is the y value when we go to graph things. And then this stuff over here, this 3x plus 4, is the function. That's going to be the machine that we're going to use. So on this next page, let's actually find what this function machine is going to do. So our function is going to take the 3x plus 4 and do something with the numbers we plug in. So let's do f of 2. So when you have this right here, we would say this out loud as f of 2, or the function of 2. So we're going to take 2 and we're going to plug it into this function. If I do 3 times 2 and add 4 to it, I'm going to get out 10. So this function, put in 2 dot out 10, we can write it as f of 2 equals 10, or as an ordered pair. I plugged in 2, I got out 10. We can do the same thing for the other one, f of negative 1. If I plug negative 1 in here, I'm going to do 3 times negative 1 and then add a 4, so I'm going to end up with 1. So again, I could write it as f of negative 1 equals 1, or I could write it as an ordered pair. And the whole reason we use function notation is so that we can see the answer, like this 1 is the answer, but we can also see what we plugged in to get that answer. So that's why function notation is important. So you're going to have to make a table from a function rule. So here's an example. Gave you a function, f of n, instead of f of x, same kind of thing. And then they used 1, 2, and 3 as domain values. So remember, we talked about domain are your inputs. And it's usually x. And our range is what we get out. So range is outputs, which is usually our y values. So make a table for y equals 8 minus 3x. And now this isn't in function notation, but we could just as easily write this as f of x equals 8 minus 3x. And remember, the only real difference here is that if we write it with f of x, we know what we plugged in to get our answer out. So let's set up a table. I'm going to plug in something for x. I'm going to have my function, which is 8 minus 3x, and I'm going to get something out, f of x. So it told me to use 1, 2, 3, and 4 as my domains. So let's plug that in. 8 times 3 minus 1, that will give me out 5. 8 times 3 minus 2 will give me 2. 8 times 3 minus 3 will give me a negative 1. And then finally, 8 times 3 minus 4 will give me a negative 4. So for all of these, I could write f of 1 equals 5, or f of 2 equals 2, f of 3 equals negative 1, and f of 4 equals negative 4. So I know I plugged these in, and I got these out. Last thing, find the range of each function for the domain. So they're telling you, use these numbers as your inputs and tell me what you get out. So the very first one, f of negative 2, we're going to plug that in, and we get negative 8. F of 0, plug that in, and we get negative 6. F of 5, plug it in, we get negative 1. So our range for this function, we write some squiggly brackets, and then we list these numbers that we got. Negative 8, negative 6, negative 1. That is the range that corresponds with that domain. I'm going to have you do these two for your can you prove it. So that's it. You should be able to identify whether something's a relation or if it's a function. And then I evaluate the functions. So do those 4 problems that I left for you and this final one here. Make sure you write down any questions you have and we can go over them in class tomorrow. Have a good night.